Okay, so welcome to our next video. Now, just by the nature of these videos, they're going to be very short because my internet cannot upload a lot of data, unlike the school's internet. And secondly, I think some people will find it easier just to click through shorter videos rather than go through long videos. Now, this is Monday's lesson that we missed out because school was closed because of the storms. So let's just quickly go through it. What we're learning about is higher differentiations, or derivatives, And basically what this is if we take a differentiation, if we have something like y, we can make it into y dash. We can differentiate that again to the second derivative, which is y double dash, then y triple dash. And this can keep going on and on and on. I don't think we're going to do something to the y to the infinity. I don't think we're going to differentiate to that. But we can differentiate multiple times. The thing is, we have different notations. All of these are the same. They're just different things for y. Oh, hang on. I've stuffed up here. That should be y. Let me fix that. Okay, there we go. So y dash, we can use this as simple notation. Fx is a function of x, and we can differentiate that to f dash x, f double dash x, f triple dash x, and keep going. Then we can have y, not dy dy, and differentiate that once. Now, just to help you understand what this is, I'm going to write it out in its old form. The differentiation of y, that is, the differentiation of y with respect to x. That is, we're differentiating the function y with respect to the variables of x. That's what we're doing. So if we were to have some kind of function, let's say that, we're differentiating y. That is all of this with respect to x, these variable components that we don't know yet. But that's what this notation is doing. And you'll sometimes see it as d, and sometimes you'll see it as this funky little d. That is just a Greek letter, I believe. Now, if we're looking at this, let's do it this way. In some examples, and we're going to differentiate this twice. If we have this function, okay, x to the power 3 plus 2x minus 2, and we differentiate that, we are bringing this 3 down to the front, and we're minusing 1 from there. We are getting rid of this x and making this 2, and this doesn't have any component of x. And if we're differentiating this with respect to x and there's no x there, that is going to just go away. So what we get here in our first differentiation, the 3 has come down and we've minus 1 from that, so we get 2. Our x has gone away and we're left with our 2. So this is our first differentiation of this function. If we differentiate this, so differentiating our first twice, y double dash, we're going to have our 2 come down and it's going to multiply with our 3. So that's going to be 2 times 3, which is going to be 6. We're left with our x. And then our 2, there's no x here, there's no component. So if we're differentiating with respect to x and there is no x, again, that's going to be eliminated and we're left with this. If we graph these, we're going to have something like this. If I can get everything on the page, hopefully. Our first one, I'll have to go down, I'll have to scroll, is going to be a cubic, which cuts through 2 and then starts to curve back up again just before 1. I know that's a very crude drawing, but you get the point. That's what our first function looks like. If we differentiate this, it actually becomes a parabola. Very steep parabola. And if we differentiate that, we're going to have a linear function, which is just a straight line. Okay? Now, that's pretty much the premise of this upcoming chapter. There isn't a lot to it. However, there are some fiddly rules which comes with differentiation that we have done before, but I think I want to recall. And there are basically what differentiation is. Okay, so let's just quickly go over that. So if we have y and we have x to the power of n, if we differentiate that, it's going to be y dash. Our n comes down to the front, and we minus 1 from our indice. That is basically what we're doing in our previous examples. These next 3 rules are instances where our function and our problem is constructed in a certain way, and we have to use these rules to differentiate it. Otherwise, we just can't do it. Okay, so these are very important. These are on your cheat sheet. However, they are written very differently on your cheat sheet. Oh, phone's talking to me. So the first one I want to quickly go over is if we have something like this, y equals 2 components times each other. Now we use u and v. I'm not entirely sure why we use those letters, but we do. Maybe because we don't use them anywhere else in mathematics. U and v. Okay, if we are differentiating the product of 2 components which both have x in them, or are just times by each other, we're going to go y dash is u times v dash plus u dash times v. Now, this is the traditional way of writing it. Now, I'm going to teach you a little trick that my tutor taught me. Is the way I like to write it out is v u dash plus u v dash. And the reason for that is to help me with my next one. Okay? If we're given a function where y equals u over v, well, if we differentiate that, we get this rule, v u dash minus u dash v dash, all over v squared. Okay? These will make more sense once I do an example. The reason why I've changed this one up here is because it's the same as here. If I just remember v u dash comes first, well, then I know what's going to come first in the quotient rule, because this is strict. This is not, because this is just plus. It doesn't matter which order it goes in. This has to be this one first. So the quick little rule that I remember to make sure I don't get confused in an exam and I switch this up because these are different is I always do v u dash first. Okay, in both instances, in the product rule and the quotient rule. Okay, that's just a little hint. You don't have to take it. If you want to stick to your reference sheet, you're more than happy to. I'm more than happy for you to do that. Now, the chain rule. Now, I'm going to say this is a lot easier to do than to explain this bit of mess. Essentially, if we have a function and we have a component outside and then we have a bracket with some other component inside, if we differentiate this function, it's going to be the outside differentiated, which is this f dash, times the differentiation of the inside, times by that. That would be a lot easier with an example, which I'm about to do. I hope I haven't overloaded you or stressed you too much. I know these are a little bit overwhelming. Without an example, they are, but we'll cut that into the next video.